All right, apes, part 2 of heat transfer. So what we're going to discuss in this lecture is describe how air moves in the atmosphere. So air has 4 properties that determine how it's going to move. The first one is density and pressure. We'll go over each of these as we go along. So density and pressure. Most of the atmosphere lies pretty close to Earth's surface. We know that's in our troposphere. And that's because some of those air particles are a lot more dense and so heavier. So those things are sinking to the surface as the less dense air then is rising. So this is actually part of the reason why hot air balloons are able to rise. Air pressure and the density of the air in the balloon play a huge part in how that hot air balloon is going to work. So the air that surrounds us is composed of a lot of different elements. More specifically, nitrogen, the majority nitrogen, oxygen, and hydrogen. In those gaseous states, they fly around, they bump into each other, but they move freely. Every time they interact, they push using a tiny bit of energy. That energy builds because there's millions of particles in the atmosphere and they're constantly bumping into each other. So because that energy builds up, that's what creates our air pressure. The air pressure at sea level is around 1 kilogram per square centimeter. As you go up in elevation, it'll change. So moving away from sea level, the air pressure tends to decrease. That's why it's so difficult to climb Mount Everest. It's not necessarily the grueling task of climbing a mountain as much as it is Mount Everest being the tallest mountain on our planet is so high up that that air pressure is so low. That's why climbers who make that attempt have to use a pressurized air to help them breathe that air into their lungs. They would not be able to do that otherwise. So how does this relate to hot air balloons? The difference in air pressure can cause an upward movement or buoyant force. There tends to be less air pressure above an object than below it. So because of that, the hot air that's created inside of the balloon takes advantage of that lower air pressure above it to lift off the ground and start to fly. So whenever that air is warmed, the molecules are moving apart, they're separating, and this creates a lower density for air. So that less dense air then rises. The cold air is displaced and then sinks. This movement of air is called a convection current. So in talking about convection current, that atmospheric pressure is always changing. So you'll always have hot air rising and cold air descending. In the case of a high pressure system, high pressure has more particles closer together and therefore is more dense. So high pressure systems are related with cold, dry, descending air, as opposed to low pressure system where there's a greater space between air particles, and so there's a lot more freedom of movement, so there's lower pressure. That low pressure tends to be warm air and so is rising and often creates a situation where that warm rising air condenses and then forms clouds and precipitation. So with low pressure systems, there often tends to be storms, precipitation of some sort. With high pressure systems, it's usually cold, dry air, and usually pretty sunny as well. So the way air and water kind of move and flow, they move from high pressure areas to low pressure areas. So this change in pressure across a horizontal distance is referring to a pressure gradient. The greater the difference in pressure, the shorter the distance there is between them. And that steeper gradient is what creates strong currents and wind. So the movement of air across a pressure gradient parallel to our surface is called a wind. And our winds are generally named for the direction that they come from. So when you hear the word nor'easter, which we had a couple of weeks ago, that air is coming from the northeast and wrapping around, moving south. So here's an example of an isobar map. When you look at this, you should be able to, as a meteorologist, tell where the winds are coming from, how strong they are, and whether or not, based on the pressure systems, if there's rain or if there's going to be a bright sunny day. So if you look at this map, you can obviously tell where those rain or precipitation systems tend to exist, and that's around those low pressure systems. If you look at the very left upper corner of this map, you can tell those isobars are really, really close to each other. Up in that corner is a low pressure system. The closer they are, if you remember, the greater the force and the greater the wind speed there's going to be. So up there is a pretty strong system that's moving from the Pacific or from the Alaska coastline to that Pacific coastline, Washington and Oregon. So different types of pressure systems or centers. A high pressure system is typically known as an anticyclone. That's because it's moving clockwise. So that cold air is descending and moving outward in a clockwise direction. This is something that you should recognize. Low pressure systems are called cyclones. That's often the reason why hurricanes are also called cyclones. That air in a hurricane is moving counterclockwise in the northern hemisphere, which causes an upward lift of warm air at its center that wraps around and rotates in this direction, counterclockwise. So this is just an example mentioned earlier that convection currents happen in a lot of different places within our mantle as ocean currents, but also as sea breeze and land breeze. In this example for the sea breeze and land breeze, during the day, there's a lot of hot, warm air on the land as opposed to in the ocean. So that warm air is rising over the land and then moves out towards the sea where it's cooler, descends over the water, and then creates that sea breeze on land. That's why when you're at Assateague, if you've ever experienced that sea breeze, it's coming off during the day. That's why you don't get any of those mosquitoes, thankfully. But at night, that wind direction changes. The air over the land cools, so descends and moves towards the ocean where that water is going to be warmer. That ocean water has trapped that heat during the day, So it's warmer than the air around it, and it rises. Definitely don't want to be at the beach overnight. That's when you get all those mosquitoes. So the second cause for air movement, or the direction of air movement, is water vapor capacity. As warm air rises, it has a greater capacity to hold water vapor than cold air does. It's that water vapor that transports a lot of the large quantities of heat from the Earth's surface into the atmosphere. It's part of the reason why those tropical regions get so much more precipitation than, say, our area. Gas as a vapor cools at altitude, turns into water droplets, and then falls from our clouds in water or ice. The maximum amount of water vapor that the air is able to hold at a given temperature is called its saturation point. When the temperature decreases, its saturation point also decreases. Water vapor is going to condense into a liquid, clouds form, and then precipitation happens. Saturation point is related to humidity. So as you reach that saturation point, you have an increase in moisture in the atmosphere, which increases the humidity. The third cause for air movement, the way air moves, is latent heat release. So the sun is evaporating water from the surface, converts it into water vapor that enters the atmosphere. In the reverse process, when water vapor condenses into a liquid, it releases heat known as latent heat release. It's important because it means that whenever water vapor in the atmosphere condenses, the air becomes warmer, and this warm air then rises. The fourth concept here is the concept of adiabatic heating or cooling. It's a condition in which heat does not enter or leave the system that we're talking about. So a rising parcel of air is going to expand. It always expands. As that parcel expands, it's also going to cool as it goes up into the altitudes. So there's two types of ascent. There's dry adiabatic heat and moist adiabatic heat. That rate of cooling with altitude is dependent on the process called lapse rate. So connecting these concepts with adiabatic heating, when that air parcel contains water vapor rises and then cools and condenses, the release of heat is that latent heat of condensation. Which is also then related to humidity. So here are the definitions of these two concepts. Adiabatic cooling is the effect as air rises, the pressure decreases and it expands. With adiabatic heating, as air sinks, the pressure is increasing and the air decreases in volume. Okay, so back to this idea, putting all of this together, air movement and these convection currents. Atmospheric convection currents are global patterns of air. And this is initiated by In the previous video, we talked about the unequal heating of Earth. So this is what causes those convection currents. And the Hadley cells are that global movement of air between latitudes. So here's that example of the Hadley cell. We're over the tropics, and that hot air is rising. And once it gets to the certain latitude, then it condenses and cools. So as it cools, it's also releasing that moisture. At a certain altitude, that air is super dry, it's become cold, and so it descends. It takes 30 degrees latitude for that hot air to rise, cool, and then descend. Oftentimes at those 30-degree latitudes, that's when you have those hot, dry deserts. One concept that you're going to need to know is the intertropical convergence zone. That's where that cold air descending to the surface reheats, moves back towards the tropics, and at the point where the hot air is converging or coming together is that intertropical convergence zone. So that hot air is coming together from the north and south and rises at that intertropical convergence zone. There's also a polar cell. These are the convection currents that are formed by air that rises at 60 degrees north and south and then sinks at the poles 90 degrees north and south. That cold air that's descending is creating a completely different type of desert. At those poles, the north and south poles, they're actually known as cold deserts. There is not a lot of moisture in the air, and so there's not a lot of precipitation, but it's super cold. So that's the reason why there's a lot of ice, there's a lot of snow. It's formed by the water around it freezing, not necessarily because of precipitation. So another concept that goes into this air movement is the rotation of the Earth, which causes the Coriolis effect. So as the Earth is rotating on its axis, it's moving faster at the equator than at other latitudes. So that faster rotation speed causes a deflection of objects moving north and south. That deflection of objects, like air, is known as the Coriolis effect. So as you can see at this diagram here on the right, the deflection of air in the northern hemisphere occurs to the right. In the southern hemisphere, that deflection is occurring to the left. Oftentimes this is related to the reason why the water in toilets are rotating in the opposite direction than in the north and south hemisphere. The effect of this is when you're in a plane, or like this ball here that's being thrown from the North Pole, when you're in a plane, you have to create a different path to fly against the wind than you would have normally. So you're not going to be flying in a straight line to get from one destination to another. You have to actually have an arc to your path to be able to reach your destination where it will be as the Earth is rotating. So these prevailing winds around the world are produced by a combination of those convection currents, like the Hadley cells, as well as the Coriolis effect. So here are these global winds occurring at high and low pressure systems. Trade winds are one of them, they're occurring from the equator to 30 degrees north and south. In our region, we're in the prevailing westerlies. So the air is moving, say, from California to the east. So the air is moving from the west to the east. That's why they're known as the westerlies. Here they are. So the prevailing westerlies are occurring at both 30 degrees to 60 degrees north and south of the equator. And again, we name the winds from the direction that they're coming from. So storms, winds, all of those pressure systems are moving across our country from the west to the east. This is just a diagram to wrap all of this together. You've got the Hadley cells here and along the equator, and the polar cells again here from 60 degrees to 90 degrees north and south. We have our trade winds, or our prevailing easterlies, the prevailing westerlies between the 30 and 60 degrees north, and the polar easterlies from 60 to 90 degrees north. This diagram here includes the intertropical convergence zone, which fluctuates depending on the time of the year and how much or where the solar radiation is coming from. And that is what this intertropical convergence zone is, where that hot air is rising for that Hadley cell and producing that precipitation. This all together, all of those factors together, is what's contributing to our Earth's major climatic zones. So we've got polar, temperate, and tropical. So we're talking about in class the different factors that contribute to these climate zones, to the different locations of biomes across the globe, and we'll continue learning a little bit more about that as we go through our biome projects.